Alright, so hopefully everybody has turned in their homework. If not, you have about 60 seconds left before the assignment closes, so make sure you turn in your homework assignment. I'm not going to post new homework today. We'll get a new assignment on Monday and go over it then, along with reviewing the homework that you just turned in. Zoom on phone, that's always good. It works. Yeah, people, we were talking about CAPTCHAs earlier. People seem to be having issues with those. All right, so we'll talk about homework on Monday, but any general questions about induction? We're going to go through more examples of induction today, but any sort of general questions about the process? A few people submitted their homework early, and I gave some feedback on that. So questions about that or anything related? All right, well, let's just continue with more induction. So we've seen a number of different examples of using mathematical induction. We've seen some mathematical examples involving, expressions of n. We've seen some examples involving inequalities. And we've seen some kind of non-mathematical examples like postage stamp problems where we can make a certain postage out of certain denominations and show that that's always doable. And we've seen some decidedly non-numeric examples like tiling floors with L-shaped tiles. And these are all fair game for mathematical induction. And there's a lot of other things we could demonstrate and prove to be true with mathematical induction. So for example, when we did set theory, we looked at finite sets and we said the cardinality of the power set of a finite set is 2 raised to the cardinality of S. In other words, if S is finite, the number of subsets is 2 raised to the number of things in S. So for example, if S contains 3 elements, then the power set of S contains 2 to the third is 8 elements. In other words, there's 8 subsets of this set. And people observed, and I confirmed this observation that, for any finite set, if it contains n elements, then there are 2 to the n subsets of that set. And that does, in fact, turn out to be true. But we can actually prove it, and we can prove it with mathematical induction. So I won't do this as a full-on formal proof, but just to give you an idea of how we would do this. So let P of n be the proposition for any set S with cardinality equal to n. The cardinality of the power set of S equals 2 to the n. And we would like to prove let's say P of n for all n bigger than or equal to 1. It's also true for the empty set. Let's just start with n bigger than or equal to 1. And we structure this exactly like every inductive proof we've been doing. We would start off, we'd state the hypothesis, we'd do a base case, which is to look at P of 1. Well, if S is an element with only one set, right, S is a set containing, a single element, well, we can write the power set of that. It's the empty set, and it's the set containing X. And the cardinality of this power set is thus 2, which is 2 to the 1, which is 2 to the cardinality of S. So the base case, as usual, is just a verification. And that's pretty easy to show. But what would we do for the general case? And again, I'm not going to do this as a formal proof, but I want to look at that intuitive part, that leap that needs to be made as we're doing a formal proof. So let, B for big be a set with cardinality n plus 1. So B is a set containing n plus 1 elements. And we assume that our proposition is true for n. All right, here's what we can do. Let A be the set of all subsets of B take away some element. So pick some element B0 in B. Doesn't matter which element. We know that it has cardinality n plus 1, and n is bigger than or equal to 1, so there are elements. So pick any element you want. Just fix it for the whole proof. I'm going to call it B0. And let A be the collection of all subsets that do not contain B0. And let B equal the set of all subsets of B such that B0 is contained. I shouldn't call it B. Let me call it C. And let me not do the fancy subtraction. Let A be the set of all subsets of B such that B0 is not contained in that subset. All right, so what are we doing? We're taking our set B, we're forming two collections of subsets, all the subsets that contain this one element B0 and all the subsets that do not contain that element B0. And I think you'll agree any subset of B either contains or does not contain B0. And any subset that contains B0 is not a subset that doesn't contain B0 and vice versa. So this is the collection of all subsets, right? In other words, the power set of B is the union of these two sets. This is all subsets. These are subsets that don't have B0. These are subsets that do have B0. And now you use your inductive hypothesis, right, to show that the collection of all subsets, since this is a set of order n, you can show that the number of things in here is 2 to the n, and you can show that the number of things in here is 2 to the n. And so the total number of subsets is 2 to the n plus 2 to the n, which is 2 to the n plus 1, and that'll prove P of n plus 1. Now there's a lot of detail to make that formal, but intuition-wise, right, what we're doing is we're taking our notion that, here's a set with 3 elements. Number of subsets is 8. If I added a 4th element, B0, for every subset I had of this, I could either use that subset or I could take that subset with B0 tossed in. Well, I have 8 subsets just containing those, and I have another 8 subsets that I get from subsets of this with B0 tossed in. 8 and 8, 16, that's 2 to the 4th. And nothing magic about 8 and 2 to the 3rd and 16 and 2 to the 4th. I could do that for any finite set. And there's lots of cases where we can apply this kind of inductive reasoning. So let's look at DeMorgan's theorem. So that's DeMorgan's theorem on 2 sets. And we're going to take that as being true. But it turns out that we can do this for any number of sets. A0, union A1, union A2, union A3, union A4, complemented is the intersection of the complement of all 5 of those sets. Well, let's prove DeMorgan's theorem for 3 variables. Prove A0 union A1 union A2 complement equals the intersection of all 3 complements. And this is pretty straightforward to prove. I'm not going to say this is equal to this and then prove something, right? This is what I'm trying to prove, so I'm not allowed to write this as part of my proof unless I proceeded with the words, you know, what we want to prove is this, which is what I've done. But here's what we can do. I can say the complement of this is the same as the complement of this. That's just associativity, right? I'm taking these 2 things and saying take the union first, and then union with A2, and then take the complement. So that's just associativity. And now I'm going to use DeMorgan's theorem. Why? Because I have one thing unioned with another thing, and I'm taking the complement. And DeMorgan's theorem says that's the same as the complement of the first intersected with the complement of the second. So that's associativity, that's DeMorgan's theorem on 2 variables. And now I'm going to apply DeMorgan's theorem again to this piece and say this is A0 bar intersect A1 bar intersected with A2 bar. That's again DeMorgan's theorem on 2 vars. And then I'm going to do associativity and just say that's A0 bar intersect A1 bar intersect A2 bar. So that's just, you know, playing around with it, and the real trick here is, you know, group these 2 things together and apply DeMorgan's theorem on this union that to get, you know, the complement of this, and then use DeMorgan's theorem again. Well, if I wanted to prove this for 4 variables, I can do exactly the same thing, right? I can say that for 4 variables, it's, you know, the complement of this union with A3, and then I can replace the union of this, the complement of this union with this thing because I've got DeMorgan's for 3 variables, right? So proving that the 6 variable version of DeMorgan's theorem works is very straightforward but tedious. First you show that it works for 3, and then 4, and then 5, and then 6. Mathematical induction would let us do this for any integer n bigger than or equal to 2. And it lets us take this approach that we would use to show it for a particular n and generalize it in the same way that we would generalize it when we were trying to show, for example, the 4 variable version. So I don't know how DeMorgan proved this, but this actually comes out of other branches of mathematics. If you look at what are called homomorphisms, homomorphisms of semigroups and monoids is the song lyric waiting to be put to music in my head. This is an example of a homomorphism between 2 mathematical objects that are called semigroups. And the flipping from one type of operation to the other when you apply the complement, that's DeMorgan's theorem. And I don't know if this came out of, you know, a mathematical footing like that, or if it was discovered in the realm of Boolean algebra or what. But there's similar versions of this throughout lots of different areas of science. Not to underweight the brilliance of DeMorgan, because I'm sure this was a breakthrough when he did it. All right, so I want to do a completely non-mathematical application of mathematical induction. This is something called an odd pi fight. And so I don't know if you've ever had a pie fight or not, but basically the idea is, you know, a bunch of people have pies and they throw them at each other. So pie in the face kind of thing. And we can do mathematical induction and analyze a certain type of pie fight. So here are the rules for this setup. Each person holds a pie. On command, so this is when the person running the party says go, each person throws their pie at the person closest to them. And there has to be a unique person closest to them. So we have an additional rule. Distances between people are unique. So no two people can be standing exactly the same distance apart as any other two people. If you make a table of all the distances between all pairs of people, a number can appear in that table only once. And that's a minor requirement, right? If two people happen to be standing exactly the same distance apart, one of them just has to move a millimeter, you know, closer or further, so that we have unique distances. All right, so you got unique distances between people. Each person's holding a pie. When the whistle blows, everybody throws their pie at the person who is closest to them. And the question is, does anyone survive? And by survive, we mean, you know, not get hit by a pie. And so here's the theorem. No, the pies are definitely not bombs. I like to think of them as chocolate cream pies, actually, because there's like nothing bad about getting a chocolate cream pie in the face as far as I'm concerned. Okay, so here's a theorem. If you have n people participating in this, if n is odd, then someone survives. So this is sometimes called the odd pie fight theorem. So if you have an odd number of people in the room and you follow this game, there'll always be at least one person who is not hit by a pie. Or a boxing glove on a spring. Or a pie containing a boxing glove on a spring if you're going like Three Stooges. Yeah, I'll go with fluffy chocolate cream pies. Can you tell I'm hungry? I haven't had lunch. All right, so how do we prove this using mathematical induction? Let P of n be the proposition in an n-person pie fight, there is a survivor. And we want to prove P of n for all n bigger than or equal to 3 where n is odd. So we're going to use a slightly different version of induction here. We're going to prove a base case, P of 3. And then our inductive step is going to be a little different. We're going to prove that P of n implies P of n plus 2, where n is odd and bigger than or equal to 3. Right? We're only trying to show that the proposition is true for odd n. So we're going to show it's true for 3, and then our inductive step will say if it's true for 3, it's true for 5. And our inductive step will say if it's true for 5, it's true for 7, and we can induct up to any odd number. And sometimes you see this with inductive proofs. You don't always start from 1. You don't always go from n to n plus 1. Now, if we wanted to go from n to n plus 1, we could do that. We could make this a proposition about a 2n plus 1 person pi fight, and n could go from 1 to 2 to 3 and so on. But I want to keep this non-mathematical, right? So I've got a plus sign in there. Other than that, we're going to keep this kind of hand-wavy. All right, so first step, the inductive case. Let's prove P of 3. And this takes a little more work than some of our inductive steps. But let's just think about what this looks like. So you have 3 people in a room. Let me label them A, B, and C. And the distances between them are unique. So there's one distance here, there's a distance here, there's a distance there. One of those distances will be smaller than the other 2. Whichever distance that is, the 2 people who are separated by that distance are closest to each other. For example, the way I've drawn this distance is shorter than either of those distances. That means B and C are closest to each other, which means B is going to throw their pi at C, because they're closer to C than they are at A. And C is going to throw their pi at B, because C is closer to B than C is to A. So now 2 pi's have been thrown. A has not been hit yet. A has 1 pi to throw. You can't throw a pi at yourself, so you're going to throw it at either C or B, whichever one is closer, and in either case, A is going to be the survivor. So P of 3 is true. So now let's induct. So suppose P of n is true. And now you have n plus 2 people and n plus 2 pi's. Alright, so here's our room. And here's a bunch of people. So pick the 2 people closest to each other. I'm going to label these people, these n plus 2 people, I'm going to label them person 1, person 2, person 3, person n plus 1, person n plus 2. This is probably the only time you'll see me indexing something that doesn't start from 0. So these are the people, and I'm just going to call the 2 people who are closest to each other person n plus 1 and person n plus 2. Yeah, definitely. Okay, so suppose, here's person n plus 1, and here's person n plus 2. And the distance between them is smaller than the distance between any other people in the room, right? The distances are unique. It's a finite set of distances, so we can sort them smallest to largest, find the smallest distance, and the people separated by that, those are these people I'm calling person n plus 1 and n plus 2. So again, they're going to throw their pi's at each other. We're going to run this fight sequentially. Instead of blowing the whistle and having everybody throw at the same time, we're going to stagger it. That's not going to affect the outcome. We're just going to have people throw their pi's one at a time. And we're going to start with these 2 people throwing their pi's. Now, after that event has happened, what is our situation? We have n people in the room, and we have n pi's. And there are 2 possibilities now. Possibility 1. Someone who still holds a pi throws it at person n plus 1 or person n plus 2. So, right, these two people are done. They've thrown their pies. There's n people left in the room holding pies. The first possibility is at least one of those people might throw their pie at one of these two people. If that's going to happen, then go ahead and let them throw their pie. And now we have n minus 1 people holding pies, n minus 1 pies. But how many people have not been hit by a pie yet? So far we have n survivors. Right? We had n people, none of them hit by a pie. They were holding a total of n pies. One of them threw their pie at one of these two who had already been hit. So these n people are still all survivors, but now there's one fewer pie. Well, if you have n survivors and n minus 1 pies, there's no way each one of these people can get hit. That's another induction argument we can make. But if there's only, 9 pies in the room and you have 10 people, not all 10 people can get hit. Somebody's going to survive. So in this case, we definitely have a survivor. But there's another possibility, which is the more interesting one, which is those n people all throw their pies among those same n people. In other words, we started off, these two people threw their pies at each other, and now they're completely out of the game. And none of these other people are going to throw their pies at either of these two, so these n people are going to throw their pies amongst themselves. Well, guess what? According to P of n, somebody's going to survive that. Because that's a pie fight with n people holding n pies, throwing them at each other. That's the exact setup for an n-person pie fight, and because we're assuming P of n is true, somebody's going to survive. And since those are the only two possibilities, in all cases there is a survivor, therefore P of n plus 2. So we've proven a base case, we proved the inductive step, therefore P of n for all n bigger than or equal to 3, where n is odd. So yeah, that's a mathematical induction word problem. I mean, they're all word problems, it's just some of them involve more words than equations. Some of them seem to involve no equations, some involve mostly equations, but it's all kind of the same thing. So that's an example of an inductive proof that has very little to do with mathematics, but is still using the idea of induction. And this is not something I would ask you to come up with on a test, right? But I want you to see different examples of this, and I want you to increasingly think about, as you're trying to understand different things that we learn in computer science, be it DeMorgan's theorem or the height function for a tree or the balance function for a tree. Think about how could I prove that this is actually correct? And if you can see that it's correct for a particular case, and you can figure out how to go from a particular case to a slightly more complex case, and from there to a slightly more complex case, think about how you could generalize that. And induction is the thing that lets us capture that sort of, intuitive understanding of why this is always true, and lets us formalize it. All right, so sidebar, question for PA1, go for it. For the list, I only put one combination of prime numbers for each number because some of the numbers have several. Yeah, you only need one, and I recommend only one. For a number around 5 million, there's going to be a lot of ways you can write it. But as soon as you find just one way to write it as a sum of two primes, write that out, go on to the next even number. You're welcome. All right, so let's talk about the color of horses. So, you know, we know what horses are, right? And they presumably come in lots of different colors, right? There's brown horses and there's white horses and you know, depending on where you live, there's purple horses and there's horses with stripes and all kinds of stuff. But we're going to prove that none of that is true. We're going to prove that all horses are the same color. And we're going to do it using mathematical induction. All right, so let P of n be the proposition in a group of n horses, all those horses are the same color. And we're going to prove this is true for all n bigger than or equal to 1. All right, what's our base case? P of 1 says, you know, in any group of one horse, all horses are the same color. And that's absolutely true. If I have, you know, a field and there's one horse in it, are all horses in that field the same color? Yes, because there's only one horse in there. Right? In my apartment right now, all people have the same birthday. Well, I'm the only person in my apartment right now, right? So everybody who's in my apartment has the same birthday. So P of 1 is definitely true. And I'll tell you up front, this is not where the problem is. Okay, P of 1 is in fact true. Obviously, we're going to run into a problem somewhere because we know that not all horses are brown. But this is not where I'm slipping something past you. So the base case is perfectly valid. So let's do the inductive step. And if you've seen this before and you already know what's going on, then I'll ask you not to spoil it in chat quite yet, because it's fun to think about. Okay, so inductive step, prove P of n implies P of n plus 1. Okay, so first, we're going to assume P of n. That's the hypothesis. All right, step 2. So we're going to go into picture land now, right? Consider a group of n plus 1 horses. So I'm going to line these horses up. I'm going to give them some carrots or something so it's consensual. And they're going to eat their carrots very happily, but they're going to do it while standing in a line. And I'm going to put a tag on the ground in front of each of these and label each of these, you know, horse 1, horse 2, horse 3, horse 4, up through horse n minus 1, horse n, and horse n plus 1. All right, so I've got n plus 1 horses. Well, remember, we're assuming P of n. So if I form a subset of n of these horses, they should all be the same color. So I'm going to take the first n horses. And all the horses in here are all the same color as each other. I'm also going to take the last n horses. That's also a collection of n horses, And so since P of n is true, these are all the same color. Well, these n horses are all the same color as each other, and these n horses are all the same color as each other. And there's only one way that can happen, which is if all of these horses are the same color. Because if these are all brown, and these are all brown, right, and these have to be brown because these are brown, so that one's got to be brown, so they're all brown. And therefore, P of n plus 1 is true. So P of n implies P of n plus 1, therefore P of n for all n bigger than or equal to 1. And that's what we were trying to show. All horses in a group of n are the same color for any n bigger than or equal to 1. So the question is, what's wrong with this proof? I guess the first question is, are all horses the same color?
No.
Okay, I will take that as given. And there's more than one horse in the universe. So what's going wrong here?
You're assuming each horse is, well, no, you're assuming there's only one color horse in the universe when in fact there's multiple.
I'm not assuming that, though. I'm saying suppose that in any group of n horses, all those horses are the same color, and we're proving, therefore, in any group of n plus 1 horses, they're all the same color. And then we're using mathematical induction, combining that with a base case and saying, therefore, this is true for all numbers of horses. But when we do a mathematical inductive proof, at this point, we never know if P of n is true. We're only proving if that's true, then it's true for n plus 1. But that right there does not imply that P of n is true. We're saying if it's true, then that's true. But then when we put that together with the base case and we say mathematical induction, then we get P of n for all n. But we don't actually need to know that this is true. And in fact, we usually don't. If we did, we wouldn't be doing an inductive proof at all. So it's okay to make that assumption for n. So something else is going on here. Give you another minute to think about. Occam's razor would say that the answer is there's only one color horse.
Can you state the problem again so I can hear it one more time?
Which part of it?
I think he means the prompt.
So let P of n be the proposition in a group of n horses. All of these horses are the same color. And so we did the base case P of 1 because in a group of one horse, all the horses in that group are the same color. And then we said, well, if we have a group of n plus 1 horses, I can look at the first n and those are all the same color because P of n says they are. And I can look at the last n horses and all of them are the same color because P of n says they are. And since these horses are all the same color, and these horses are all the same color as that last horse, then all n plus 1 horses must be the same color. and therefore P of n plus 1 is also true. So I did something funny in here. And if you want to take apart an inductive, if you want to build an inductive proof, what do? You start trying to prove specific cases and try to capture what it is that you're doing to go from, 1 to 2 to 3 to 4 and so on. If you want to take apart a proof, you can do exactly the same thing. We know P of 1 is true. This argument should tell us that in any group of 2 horses, both horses are the same color. And we're actually proving that all horses in this group of n plus 1 are the same color as each other. But here's the trick. This argument is perfectly valid, right? Suppose P of 5 is true. Suppose, just for a moment, that in any group of 5 horses, all 5 horses have to be the same color. Okay, now pick 6 horses. Let's just call them A, B, C, D, E, F. Well, if P of 5 is true, then these 5 horses are all the same color. Let's say they're brown, right? If P of 5 is true, then these 5 horses all have to be the same color. And since, B, C, D, and E are brown and all 5 are the same color, then this horse also has to be brown, which means all 6 horses are brown. There's nothing wrong with that logic. That works perfectly well. The problem is I used the wrong base case. So we know that P of 1 is true. But can we use this logic to show that P of 2 is true? Well, here's the argument. Let's take 2 horses, A and B. My argument says all of these horses are the same color. All of these horses are the same color. But guess what? There's no overlap between those 2 sets. There's nothing in this situation that says A and B are the same color. So P of 1 does not imply P of 2. But in fact, if I assume P of 2, and I take 3 horses, these will be the same color as each other, these will be the same color as each other, which means C is the same color as B, and B is the same color as A, so all 3 will be the same color, and so P of 3 will be true. So P of 2 does imply P of 3, and P of 3 implies P of 4, and P of 4 implies P of 5, and so on. That's absolutely true. But we don't know that P of 2 is true, and in fact it's not. We know P of 1 is true, but my argument in my inductive step does not let us claim that P of true follows from P of 1. So there's a break in that inductive chain.
That makes sense.
So that's kind of subtle, but it illustrates the importance of the base case. And we don't give the base case its due. We say, okay, so prove P of 1, and P of 1 says this, and that's obviously true, and we go on from there. But it's actually really, really critical. So this argument that P of n implies P of n, this only works for n being at least 2. Because the reason that, saying this group's the same color and that group's the same color, therefore they're all the same color, that only works if there's some overlap between this purple group and this green group. And that only happens if n is at least 2. So we proved that P of n implies P of n plus 1, but only if n is bigger than or equal to 2. Now, if we could prove P of 2, then we could induct all the way up and show this is true for all n. But in fact, P of 2 is not true. There's no way to prove that in a group of 2 horses, both horses are the same color. And in fact, that's not true. But if it was, this argument would be valid, and we could say that, in any group of n horses, all horses are the same color. So think about base cases. If that still doesn't make sense, think about it some more, and then see if you can formulate a question where the explanation's not making sense. All right, cool. I gotta find some props. Give me 1 second. All right, I'm back. Mulling over inductive proofs. All right, so let's talk about Towers of Hanoi. So this is a very old game / puzzle. And it works like this. So the setup is you have a series of discs. They're made out of jade, and they have circles in the middle, and they come in different sizes. And there are 3 poles in a cave, and there are discs of different sizes sitting on these poles, and these discs are stacked up. And at the beginning of time, all of these discs were sitting on one pole. And there are monks who toil away day and night, moving these discs from one pole to another. And there are a few rules for moving discs. So 1, you can move 1 disc at a time. You can't just pick up a whole armful of them and carry them over, because you gotta be very mindful in doing this. So you move 1 disc at a time. You can only place a disc on a larger disc or an empty pole. So you can move a small disc over to a pole that's empty or a pole that contains a larger disc. And the goal is to move the entire stack of discs from one pole to another. And the story goes that, there's 64 jade discs of increasingly smaller diameter, and these monks are working to move the stack of 64 discs from one pole to another. And they began at the dawn of time, and when they finish moving all 64 discs, then the universe will end. And so it's like the clock of existence. And so here's today's version of Towers of Hanoi. So I have 4 discs. I have the large one, the smaller one, and then the really small one. And we're going to play Towers of Hanoi and try to move these discs from one post to another. I really should find something smaller than that big plate. So the first time I did this, I cut out circles from a Domino's pizza box and brought those in. And then I just like used those forever after. And then one year, a student after they graduated gave me a really cool little wooden Towers of Hanoi box puzzle. And I used that in lecture. That is in my office along with, you know, my statue of Albert Einstein and all of that stuff. Waiting for our return to campus. So we'll have to make do with the kitchen version of Towers of Hanoi. All right, so let me just start with a 2-disc version. And I'm assuming I've got, you know, 3 posts. So I've got one here and one here and one here. And I want to move these 2 discs from one post to another. Yeah, Einstein is probably pretty lonely. Another former student gave him to me because his girlfriend was convinced the statue was haunted and strange things were moving around in the middle of the night in his house and stuff. So Einstein ended up in the garage, and then he gave him to me, and he seemed really happy being in the STEM building. I mean, there was no evidence of haunting or anything like that. But now, you know, the STEM building's been mostly empty, so I kind of worry that poor Einstein is just standing there holding a pile of books waiting for things to happen. All right, so pair of discs right here, and we want to move to another pole. So the only thing we can move, the other rule is you can only take discs off the top, right? You can't pull a disc out from the middle. So the only thing I can move is this smallest disc up here. And I can move that, you know, to either of these poles. And now what can I do? Well, I could move this to this pole. There's no real point in that. I could move it back to the original disc. There's no real point in that. The only sort of productive move is take this, and let's move it over there. And now I can take that smallest disc and put it on top, and I'm done. And so I moved this pile from here to here, and that wasn't too hard. And let me keep score. So discs and number of moves. So with 2 discs, it took a total of 3 moves. Well, suppose I only had 1 disc. How many moves does it take to move just 1? So that's kind of a edge case. 1 disc takes 1 move. But let's look at 3 discs. All right, so how am I going to move this pile from one spot to another? So I've done this before. So let me show you a solution. So I'll go 1, 2, 3, 4, 5, 6, 7. Spooky Scary Skeletons. That's a band. Alright, 3 discs, 7 moves. Now we want to know how many moves does it take to transfer 4 discs from one pole to another. And the claim is there's a formula. So what's the formula look like? What would you expect for the number of moves for 4 disks? That's a reasonable guess.
No, wait, my math is off. Sorry.
That's okay.
It would be 15.
Okay, how'd you get 15?
I added 2 to the third.
Mm-hmm. Alright, so this previous number plus 2 to the third. So what would you get for 5? Previous number plus 2 to the fourth would be 31. The other way to see this is actually 2 to the fourth minus 1. This is 2 cubed minus 1, 2 squared minus 1, 2 to the fourth minus 1. So we might hypothesize that this is 2 to the n minus 1. There we go. So that's a reasonable looking proposition. So let's formalize that. Let P of n be the proposition. You can move n disks in 2 to the n minus 1 moves. So this is a proposition about the minimum, a sufficient number of moves to complete Towers of Hanoi for n disks. And we know P of 1 is true, because for one disk we've seen we can move one disk in 2 to the first minus 1 moves, right? That's just, you know, there's my one move. I'm done. So to prove P of n for any n bigger than or equal to 1, we've got a base case. We only need to prove the inductive step. So we want to prove that you can move n plus 1 disks in 2 to the n plus 1 minus 1 moves. Well, here's the intuition for how we can do this. Suppose we know we can move 3 disks in 7 moves. Suppose we know P of 3 is true. So 3 disks, 7 moves. And now we want to move 4 disks. And let's say I want to move 4 disks to this pole right here. Here's what I can do. I'm going to play a subset of this game. I'm going to leave this biggest disk exactly where it is, and I'm only going to look at the first 3 disks. Well, this biggest disk does not affect my gameplay. Since it's bigger than any other disk, I can put anything on here that I want. So I can use my solution for 3 disks, and in 7 moves, I can move this pile of 3 disks over to here. So for 4 disks, I can take 7 moves to move the top pile of disks to one pole. And then I can take 1 more move to move my largest disk over here. And then with another 7 moves, I can move this pile of 3 disks on top of that. 7 plus 1 plus 7, that's a total of 15. More generally, if you have n disks, if you have n plus 1 disks, you can take the top n and move it to one pole, and that takes you 2 to the n minus 1 moves. That's what P of n tells you. And then you move your largest disk to the destination pole, and then you move your other n disks to the pole with that largest disk on it, and Pn tells us that's another 2 to the n minus 1 moves, which means n plus 1 disks move in this many operations, which is 2 to the n. Minus 1 plus 1 minus 1 is minus 1 plus 2 to the n. And 2 to the n plus 2 to the n, that's 2 to the n plus 1. And we still have our minus 1. So if P of n is true, P of n plus 1 is also true. And inductively, that lets us say P of n is true for all n bigger than or equal to 1. So that proves this observation, this proposition, P of n, that you can move n disks in 2 to the n minus 1 moves. And yeah, you always have 3 poles, but yeah, if you have 64 disks, it's 2 to the 64th minus 1. So it's around 10 to the 19th operations that you would have to make to move that pile of disks. So that's a long set of operations. But that's another example of an inductive proof applied to something less mathematical than like an equation for the sum of integers and so on. All right, here's the interesting thing. More interesting thing. Oh, we don't want to see binary trees. This is an inductive proof about the number of operations that are required. But in developing that proof, we also developed an algorithm for playing this game. The way we proved that it would take 15 steps to move 4 was we said, well, let's first move 3, and then let's move the biggest, and then let's move those 3 again. And if we wanted to move 5 disks, I would first move 4 disks, and then I put my biggest disk over here, and then I'd move my 4 disks on top of that. And it doesn't matter how many disks we have. We can still do this with only 3 poles. If I know how to do this with 63 disks, and I have a stack of 64 disks, what do? I use my knowledge for solving the problem with 63 disks to move the top 63 over to here, and then I move my biggest disk down on the empty pole, and then I repeat my steps to move those 63 on top of that disk. So we can use this outline of a proof to cobble together some code. So here's a program for solving towers of Hanoi. And it's written in C, so it's got the usual stuff that makes C kind of hard to read sometimes, includes and declarations of function prototypes and so on. But the main thing is I have a function called tower, and you tell it how many disks you move, right? And you say you want to move from pole 1 to pole 2, and I'm telling it pole 3 is the third pole. And so what does the tower function do? How do we move n disks from pole 1 to pole 2? Well, here's my tower function. This is the number of disks I'm trying to move. This is the pole I'm moving from, this is the pole I'm moving to, and this is the third pole. You're not allowed to lift more than 1 disk at a time. But in effect, we're going to do just what you suggested. In effect, we're going to move the whole stack from the largest bottom disk. But we're going to have to do that 1 disk at a time. But we know how to do that if we know how to solve the problem for n minus 1 disks. All right. So how do we write a function that will move num disks from this pole to that pole? And I'm going to count the number of moves here. I'm going to increment an evil global. So if the number of disks is 1, this is easy. If you only have one disk that you're trying to move, let's just move it from the source pole to the destination pole. All right, that's our base case. That's solving Towers of Hanoi for a single disk. How do I move one disk from pole 1 to pole 2? Just take it off pole 1, put it on pole 2, and you're done. But if the number of disks is bigger than 1, we need to do something else. But it's really not that much work. So what do? We take num minus 1 disks, we move them from the source pole to the open pole, and then we move the largest disk from the source pole to the destination, and then we move those n minus 1 disks from the open pole to the destination disk. And that's it. That's the whole solution to Towers of Hanoi. And it mimics what we were doing with my kitchenette tower of disks, right? Move the n minus 1 disks on top to the pole that you don't want to end up on, and then move the largest disk to your target pole, and then move those n minus 1 disks from the open pole back to where you do want to end up. And how does this happen? Well, it's going to call itself. And, you know, if there's only one disk, it'll just move it. Otherwise, it will break it into a set of 3 operations, each of which involves solving a smaller version of the game. And my move function just prints out, you know, where I want to move from and to. So if I'm saying move, you know, from pole 1 to pole 3, I'll just print out a 1 with an arrow 3, saying make that move. And every 5 lines, I'll go out to a new line. So this is the tower function, right? That's the whole thing. And my main program, I'm just going to call it with an argument of 3 disks and ask it to tell me how to move 3 disks from pole 1 to pole 2. So I run that, there's my solution. And it tells me I made a total of 7 calls to tower, so it took 7 operations. And let me do this over here. So there's my 3 disks. And so let's follow the guideline here. So move a disk from pole 1 to pole 2, and then go from 1 to 3, and then go from 2 to 3, and then go from 1 to 2, and then go from 3 to 2, and then go from 1 to 2. Oh, I did the wrong one. All right. Go from 1 to 2, and then 1 to 3, and then 2 to 3, and then 1 to 2, and then 3 to 1, and then 3 to 2, and then 1 to 2. All right, if you want to do this for 4 disks, there's a solution for 4. If you want to do 5, there's a solution for 5. And you can make 5 disks and do this, and what you'll find is that the beginning of this is really the same thing as the solution for moving 4 disks. And then in the middle, there's a single move of the largest disk to the open pole, and then we repeat the first 15 steps to move from the open pole to the destination pole. Alright, there's the 8-disk solution. And you can see the number of moves, right, is conforming to this 2 to the n minus 1, as we expect. And so if we want to do this for 64 poles, there's your solution. And if you had 64 disks and you were following along with these moves, this would be completing the task of moving all 64 from one pole to another, in this case pole 1 to pole 2. And the code is, you know, other than the details of writing C, the guts of the code is really like 4 or 5 lines. But this will come up with, you know, 10 to the 19th moves that we should make that if we followed would solve Towers of Hanoi for 64 disks. So the number of calls to tower is the total number of steps. Yeah, I should have printed out the total number of times that we called the move function, but it's the same thing. So this is an example of the interplay between mathematical induction and recursion in computer programming, right? They're really the same thing. And you know, the base case here, which we use to say, you know, if we want to move a single disk, it takes 1 move. That's the base case in our recursive code. Right? That's this case right here. If you have a single disk, it takes 1 move. We just move it from one pole to another. And then the inductive step, proving that, you know, if P of n is true, then P of n plus 1 is true. That's the observation that, you know, we can move our first set of disks in this many moves, and then move the largest disk, and then move that same set of n disks to the destination pole. And that's this part of our function. Right? Move the first n, move the largest disk, move the first n again. And a lot of times when we come up with solutions to a problem, it mimics, you know, some sort of inductive proof, an inductive step. And so as we continue developing trees and algorithms for manipulating trees in 222, you can think about how do you know this algorithm works, and the answer is almost always you can prove it with mathematical induction. The way you prove that the height function works correctly is you show that it works for a base case. Well, that's usually the case if your argument is null. So if our tree is null, return -1. That's the height of an empty tree. So yeah, our function obviously works for the case where the height is -1. And then you have to show that if it works for a height of n, it works for a height of n plus 1. And if you believe it works for a height of n, the code is usually pretty trivial to see the correctness of. Because like the height function, what does it do? It finds the height of the left and right subtrees, it returns 1 plus the largest. And you know, one of those trees will have a height of n minus 1. And when you add 1 to that, right, you add in the hop from the root and you get a height of n. So that's just something to think about. Keep in mind as we're going through algorithms in 222, and as we're going through, you know, the next subjects we're going to do in this course. So we're going to move into talking about counting and counting arguments, and we're going to look at things called, you know, the product rule and the sum rule and things like this. And we'll be making statements about things that are true for, you know, any number of arguments. and the reason that these things will be true can be shown with mathematical induction. And then you can try to apply induction to other things. So there's some things that we can say about prime numbers that we can use inductive arguments for. For example, showing that that every number can be written as a product of primes. We can show that using induction. Pretty straightforward. It's harder to use that to actually find primes, but you can try to do an inductive proof of Goldbach's conjecture. And you can get part way there, but it's hard to actually finish it up. But it's a good thing to mess with. All right, 38 seconds left. Any last questions on that? Again, I don't expect this to be crystal clear. I just want you to see different examples of this and keep them in mind and come back to them from time to time. And you'll see more of this stuff tie together. You know, some in this course, some in the CS sequence, and some, you know, as you go on to other courses. But we're going to kind of leave induction here, and Monday we'll start talking about counting arguments and look at product rule, sum rule, pigeonhole principle, principle of inclusion, exclusion, wrapping up with permutations and combinations, binomial theorem, Pascal's triangle, all kinds of good stuff. And like most things in this course, we're going to start from pretty straightforward things, counting 1, 2, 3, 4, right? But then we'll go from there to some non-obvious, non-trivial aspects of counting and counting arguments. All right, let's see, chat question. Anything else you'd recommend for PA1 that's not included under the notes section? I don't know what all I put in the notes, but I would say basically build it up in pieces. Write a function that checks to see if a number is prime or not. That's the most complex part of the assignment. But it can be as simple as a loop that looks for a divisor, right? So write a function that takes a number n, tells you if it's prime or not. And develop that, exercise that. So write a main program, lets you type in a number, and it tells you if it's prime or not. And just feed it lots of things. Try numbers like 25 and 49 that are squares, and so on. And then once you have that, now try to write something that takes a single even number and writes it as a sum of two primes. I don't think you need linked lists for this, and I wouldn't recommend using that. You really don't need to save anything. Lists are great for organizing information that we want to save and retrieve, but you don't need to save and retrieve anything, right? You can test to see if a number is prime by dividing by things between 2 and the square root of the number, and you can do that every time you want to know if something is prime or not. As long as you're not checking too many things to see if they're prime, don't worry about trying to save your prime numbers, because then you gotta deal with dynamic arrays and stuff like that. So same with arrays, I wouldn't worry about it. I would just make a function called prime, takes an integer, gives you a 1 or a 0 to tell you if it's prime. And then go ahead and use that to write something that takes an even number and prints it out as the sum of two primes. And then take that and wrap it inside a loop for your main program. But definitely build it up in pieces. All right, that should do us for Friday. Enjoy the weekend. The sun is trying to come out. Have a good one, and I will see you on Monday.